Okay, very good morning to all. Today is our class number 27. We're going to talk about heat exchangers today. I think all of you are pretty much aware and familiar with heat exchanger. It's a device which are actually mainly being used to transfer heat across the surface so that you can have hot fluid and cold fluid passing to each other, and then at the surface the heat exchange happen because one fluid is going to lose its latent heat, then another fluid is going to take the lost heat and going to get heated up. So that's how the principle is based on the heat exchanger principle is based on that concept, and it's mainly being used throughout the industries for different purpose. There are different types of heat exchanger, as you can see. It can be starting from regenerators, recuperators, some oil condensers, IC engines, the chillers, okay, the refrigerators. So there are many heat exchanger applications. It's find this application throughout the industry. I mean, construction industry and all kinds of industry. There is a heat exchanger application. So how does this heat exchangers or type of heat exchange happens? There are many ways to heat can be exchanged, but mostly either it can be direct contact so that the fluid come in contact to each other, that is known as open heat exchanger, and then there is another is called indirect heat exchanger, which are actually classified into two different category. One is regenerator and recuperator. So let's first look into the direct contact heat exchanger. As you can see, this is a schematic diagram is given. The direct contact heat exchanger. What happens there is from one inlet, cold fluid is entering into this tank, you can say, or and then another way the heat steam is being inserted or injected. So what happens? The steam, which is actually hot, is going to lose its heats, right? So the steam is going to lose its heats, and so it gives its latent heat to the water, and then water get hot, right? And then hot water comes out from the other outlet, and if there is any non-condensable gas which comes out from this, so this is a kind of a condenser. Okay, this is kind of a condenser concept. It's a the hot fluid actually loses its heat, and cold fluid remains stationary, but actually it get heated up because the steam temperature is constant, and then it is comes out at the high temperatures. Okay, so this is a direct contact heat exchanger. This is application like cooling towers. Okay, and I would say refrigerators, not refrigerator, cooling tower, IC engines. These are actually direct contact heat exchanger. Let's look into non-direct contact or indirect contact heat exchanger. In this type of heat exchanger, heat transfer happens between two fluids, which actually passes to each other and separated by a surface, right? So regenerator is actually it's a transient type of heat exchanger, hmm, where actually what happens, hot and cold fluids passes intermittently, okay, through a space containing some solid particle. So the solid particle actually here acts as a sink and source of the heat flow, because when the hot fluid passes through this the solid particle is going to lose its heats, right? And then that amount of heat which is going to be lost by that hot fluid is going to be stored by the solid matrix. And after the hot fluid has been passed through it, the cold fluid, which again then passes through it after a certain time interval, is going to take up those heat, and then it's going to get heated up, right? So that is the concept of regenerator. It's a transient state heat exchanger, and the applications, like you can see example, IC engine, gas turbine, open hearth, and glass melting furnace, air heater, and blast furnace. Okay, as I said, the regenerator generally operates periodically. That is the transient state, and alternately it stores the extracted heat from the hot fluid and then deliver it to the cold fluid. However, in some cases, regenerators the is matrix is made to rotate through the fluid passage arranged side by side, which makes the exchanger process continuous. Because now with the evolution of industrial application, transient state or intermittent heat exchanger is not very lucrative or very cost effective. So people have come out with a strategy so that it can be make continuous in nature, so that the efficiency and the cost effectiveness can be increased. Now, how this performance of regenerator actually been affected? There are three parameters which actually control uh, the the heat exchanger I mean the amount of heat which is going to be exchanged. The mainly are the rate of absorption, the release of heat, and the heat capacity of the generating material, right? So that is very important, right? How much heat is going to be stored and how much heat is going to be lost. The heat capacity of the generating material is very important. What are the advantage of regenerators? Is having a high heat transfer coefficient, minimum pressure loss, small bulk weight, less weight per kilowatt of the plant, and then quick response to load variation, and its efficiency is quite high. Okay, let's look into some disadvantages. It's a costlier compared to recuperative heat exchanger, and there's some sort of leakage sometimes, which actually requires maintenance. So that is the disadvantage. Now comes the recuperator. Recuperator is much more advanced concept, and it's actually during recuperator, it's a steady state or continuous heat exchanger happens when actually what happens here, the flowing fluid exchange heat at either on one side or on the dividing wall. So there is some sort of dividing walls being there. So the hot fluid loses its heat, and which is going to be taken by that wall, and then it's going to exchange with the cold fluid. This type of heat exchangers, there is no mixing of the fluid, okay, which can be completely avoided. So if you have one can be oil, another can be water. I mean, different types of fluid can be, can be utilized for recuperation, okay, recuperation application. And this is much more advanced concept, and there are examples, as you can see: automobile radiator, oil cooler, milk chiller, evaporators, all kind of application, industrial application. Recuperators are being used. It has a huge advantage: is easy construction, maintenance cost is low, more economical. But the disadvantage are loss, less heat transfer coefficient, because there is some sort of heat loss happens in the wall, some sort of shooting problem because some deposits happen on the surface if you have a corrosive liquid or fluid, which sometimes hampers the performance, and then its generating capacity, heat capacity is low. But again, recuperator is, I would say, it's much more advanced and much more economical compared to regenerator. Okay, and as you can say that direct heat exchanger and recuperator are actually considered steady state heat exchanger, while regenerators are known as transient state heat exchanger, because in regenerator you have to intermittently pass the hot fluid and cold fluid, whereas in recuperator continuously hot fluid and cold fluid can be passed through. So let's look into different types of heat exchanger based on the fluid pattern. Okay, the fluid pattern can be parallel flow, like as you can see, parallel flow heat exchanger where the hot fluid and cold fluid passes in the single direction, right? So as you can see, this has been given in the schematic diagram. The hot fluid temperature is TH1. H stands for hot and C stands for cold. 1 and 2 stands for inlet and outlet respectively. So what you can see that hot fluid, the red signals means the hot fluid, and black is actually signifies cold fluid. What you can see that hot fluid and cold fluid passes in the same direction, but again, you need the hot fluid loses its heat and cold fluid gains its heat. So the temperature difference at the inlet and outlet is completely different, right? And there is application oil cooler, oil heater, water heater, and the two fluid are separated by wall. This type of heat exchanger may be called parallel flow heat recuperator or surface heat exchanger. But since this type of heat exchanger makes a large area of heat transfer, therefore is rarely used in practice, because you need a large area for heat exchanger to happen. Okay, because because as you move in the same direction, there is the fluid which are actually got in touch here are going to get heated up, and then it moves as this in the same direction. It is not going to get heated up because it's already being heated up. So you need large area, okay, for heat exchanger to happen. That's why it is rarely see, since the cold fluid and the hot fluid passes in opposite direction, as you can see here, you need a small area for heat. I mean, this is much more economical and much more efficient, I would say, where actually due to counterflow, maximum heat transfer happens from the given surface area. Hence, this type of heat exchanger are most favored for heating and cooling of fluid, because the cold fluid is going to go complete, it's going to get heated up here, but as it moves in this direction, again it is going to gain heats, right? So it actually, with the more surface area, you can have a much more higher exchange of the heat. Okay, so that's why counterflow heat exchanger is much more economical. There is another type of heat exchanger which are known as cross flow heat exchangers. As you can see, in a cross flow heat exchanger, the two fluids, hot and cold fluids, crosses one another in space, uh, usually at right angle. This is a figure 10.4, which are showing two different types of cross flow heat exchanger. The first one is hot fluid is in the separated. So this is actually hot fluid, which are actually passing in the separated tubes. Okay, and the cold fluid are actually passing on at right angle throughout the surface. Right, the cold fluid is perfectly mixed, but in the first case here, the cold fluid are perfectly mixed. So it's a mixed hot stream. Okay, and the temperature of this mixed fluid will be uniform across any section. So temperature at this junction is same because it's mixing happening, but across the direction of flow, the temperature is going to be different. So this is where actually a mixing of hot stream happen. But another is the unmixed stream. There is no mixing of cold fluid and hot fluid, and you can see these blue lines actually is called baffles. Baffles actually separates the direction of cold fluid. Okay, so the cold fluid are not going to mix to each other, and hot fluid, as I said, is uniformly flowing through this tube. So the second one is actually no mixing happen. In this case, the fluid flows by a prescribed path, and it's never mixed or it's unmixed. But the temperature of the fluid leaving the heater section is not uniform because temperature here and here might be different depending on the how much amount of heat is being exchanged at this surface. So the across this direction of flow or across this length of the cold fluid, the temperature is not uniform. Okay, but in this direction, temperature will be steadily increased. Mobile radiators, and the first example was refrigeration system. Okay, so let's look into another types of heat exchanger. This is actually shell and tube heat exchanger. Shell and tube heat exchanger actually separated by baffle, and then you can see it's a one shell and two tube. The one shell is this, and two tubes are actually, you can see here is the tubes. Okay, this is actually two shell pass and four tubes. One, two, three, four, and two shell. One shell is this, another shell is this. So shell and tube in this type of heat exchanger, one of the fluid flows through a bundle of tubes enclosed uh, uh, by a shell. Okay, the other fluid is forced through the shell and is flows over the outside surface of the tube. So what happens? The heat exchanger, since the use of multiple tube heat transfer is amply improved due to the increased surface area. Because of the number of tubes are increased, the heat transfer rate is higher compared to others. Okay. Multiple shunt tube passes are used for enhancing the overall heat transfer. Multiple shell is possible when the fluid flowing the shell is rerouted. As you can see, multiple shell, one fluid is coming and then again it's moving from another direction, right? The shell side fluid is forced to flow back and forth across the tube by baffles. Baffles are here, right, which separating the inside inlet and outlet fluid. Multiple tube pass exchanger are those which actually used for rerouting the fluid through tubes in the opposite direction. You can see the direction has been altered, right? So you can read this and then get an idea. Then we'll come to physical state of fluid. There are two different types of fluids which are actually based on the concept of fluid flow pattern, which is known as condenser, and another is evaporator. As you can see, the condenser, the hot fluid temperature remain constant. Okay, the condenser fluid remain at constant temperature because this fluid is going to get condensed. So it is temperature uniform, like TH1 and TH2. So inlet and outlet temperature is same, but the cold fluid actually which are going to get the latent heat lost by the hot fluid is going to gradually increase its temperature. TC1 and TC2 are different. So that is known as condenser. Okay. Similarly, in evaporator, the reverse concept happen. In this case, the boiling fluid, because the cold fluid is going to get hot, heated up, right? The hot fluid gradually loses latent heat, and the cold fluid can get heated up. The inlet and outlet temperature of the hot fluids are different, but the inlet and outlet temperature of the cold fluid, which is known as boiling fluid, is constant. That is actually known as evaporator because the cold fluid is going to get heated up. So this is actually pretty much the basic fundamental concept and classification of heat exchanger which I have given you right now. So now we'll move to the theoretical parts, and we're going to derive some expression. You can look at this expression, and most important is the we have to derive the log mean temperature difference for heat exchanger, mainly for parallel flow and counter flow. That is going to be discussed in the next slide. So first, let us look into some basic fundamental equations. As you can see, the red line red line signifies hot fluid, and the black line signifies cold fluid. So the hot fluid actually enters at TH1 inlet temperature and goes out at the temperature of 2. And the cold fluid inlet and outlet temperature are TC1 and TC2. As I said, H and C refers for hot and cold, and O1 do refer for or corresponds to inlet and outlet respectively, right? If we consider or if we assume m dot is actually mass flow rate, that is the amount of fluid passing per unit time. Cp is specific heat of fluid, which is given joule per kg degrees. T is the temperature of the fluid given in degrees centigrade, and delta T is the temperature difference. Then the expressions will be like this: the heat given up by the hot fluid, which is known as mCp del T, that is the general expression, where m is the mass flow rate, Cp is the specific heat, and del T is the temperature difference, which can be given by this expression. Q equal to mH Cph times Th1 minus Th2, because that is the amount of heat which is going to be lost by the hot fluid, right? Here mH is, H stands for hot fluid. Cph means the specific heat of the hot fluid, and then Th1 and Th2 is the temperature difference of the hot fluid, as you can see. So this much amount of heat which is going to be lost by the hot fluid is going to be gained by the cold fluid, which is given by this similar expression Q equal to mc times Cpc times Tc2 minus Tc1, because this amount of heat lost by the hot fluid is going to be gained by the cold fluid. Now that can be generally can be expressed by a general equation, that is the total heat transfer rate of the heat exchanger, given by Q equal to U times A times theta m, where U is actually known as overall heat transfer coefficient. I think all of you know what is overall heat transfer coefficient. We have already derived this expression in previous presentations. A is the effective heat transfer area, and then theta m is the, which are going to derive in the next slides onwards, is known as logarithmic mean temperature difference, or in short LMTD. Okay, so how this is been derived, that we are going to look. So let's look into that. Logarithmic mean temperature difference, which is most important, is actually defined as the temperature difference which, if constant, would give the same rate of heat transfer, which actually occurs under the variable condition of temperature difference. So the amount of heat amount of heat transfer which are going to happen between the hot and cold fluid actually can be expressed by this logarithmic mean temperature difference. Okay. Now, in order to derive this LMTD expressions, we need to know various parameters, like the overall heat transfer coefficient has to be constant U, the flow condition has to be steady state, the specific heat and mass flow rate of both fluid has to be constant. There should not be any heat exchanger to the surrounding, because if it happens, then the steady state condition will be violated, and there should be no change of phase. That means that cold fluid and hot fluid should remain identical in its original phase. The change in potential and kinetic energy must be negligible, and the axial conduction, that is across the radial direction along the tube of the heat exchanger, must be negligible. So these are actually all some pre-assumptions which you need to make, and then based on this we're going to make the derivation. So let's before going into the derivation, let's look into the schematic diagram. This is actually the schematic diagram which we are going to derive the log mean temperature difference for a parallel flow heat exchanger. That same can be utilized for counter flow heat exchanger, and I would urge all the students to derive the expression for counter flow heat exchanger. Just draw the picture and derive it. Same concept. You can do it as your homework, because the conditions and everything will be same. Now let's look into some fundamental difference here. Actually, the temperature difference at the inlet and outlet given by theta 1. So for a parallel flow heat exchanger, at the inlet, temperature difference will be Th1 minus Tc1, because Th1 is greater than Tc1. So by theta 1, and at the till the Th. So as you can see in this picture, we are actually defining this inlet and outlet temperature theta 1 and theta 2. So the same temperature difference, I mean, for a counter current, counter flow heat exchanger also, you can derive the expression, as I said. So if you are familiar with this, the notations which are actually given, let's go back to the slides and then derive the expression. So you can always look back this figure, and let us first consider an elementary area dA for the heat exchanger, and the rate of flow through this elementary area is given by dq u dA Th minus Tc, where u is the overall heat transfer coefficient and Th minus Tc is the temperature difference, which can be given by delta T. Now, as a result of the heat transfer dq through this area dA, the hot fluid is going to be cooled by dTh, right? Whereas the cold fluid is going to get heated by the amount dTc. So dTh and Tc actually is the differential amount of heat lost by the hot fluid and gained by cold fluid respectively. So the energy balance equation over a differential area dA can be represented by dq is minus mh Cph dTh, because mh here actually again m dot h is actually mass transfer rate for the hot fluid, Cph is the specific heat of the hot fluid, and dTh is the differential temperature of hot fluids, and it is given by cold fluid is given by m dot c Cpc dTc. Now here negative sign is given because hot fluid is losing temperature and cold fluid is gaining temperature. So that's why some for different convention, one given positive. So that can be the expression dq mh Cph dTh equal to mc Cpc dTc is equal with u dA Th minus Tc with the original equation. So DTH, you can rearrange this term, can be given by minus dq by mhcph, which is nothing but minus dq by ch, where ch is the heat capacity given by m dot h cph, given here, right? Heat capacity of the water equivalent output. Similarly, DTC given by dq by m dot c cpc, or equal to dq by cc. Here cc is m dot c cpc, or the heat capacity of water equivalent cold fluid. Now m dot h and m dot c are the mass fluid and of the fluid, and cph and cpc are the specific heat. So you can take this two equation, you can minus 1 minus 2 you can do, and then it will become dTh minus dTc equal to minus dq 1 by ch plus 1 by cc. And this is actually already given by d theta, right? Because you can say the temperature difference is d theta. As you can see, if Th minus Tc is theta, then dTh minus dTc will be d theta, right? You can given here, right? dTh and dTc. So it will be d theta equal to minus dq 1 by ch plus 1 by cc. Now the substitute the value of dq from this expression, and you can become d theta is become minus dq. So u dA dth minus dc. This expression we are just substitute here, and then it's become this expression, right? D theta equal to minus u dA times th minus dc times 1 by ch plus 1 by cc. So d theta is minus u dA theta, because th minus tc is theta, as I can say here, right? Th minus tc theta. 1 by ch plus 1 plus cc. So we can rearrange this term and then integrate within 1 and 2, that is inlet and outlet, and the area is A. So finally become ln theta 2 minus theta 2 by theta 1 minus ua 1 by ch plus 1 by cc. Now the total heat transfer between the two fluid is given by q ch th1 minus th2 equal to cc tc2 minus tc1. So 1 by ch is given by th1 minus th2 by q, and similarly 1 by cc is given by tc2 minus tc1 by q. So if you substitute the value of 1 over ch and 1 over cc in this expression, this become ln theta 2 by theta 1 equal to minus ua th1 minus th2 by q plus tc2 minus tc1 by q. You can take the 1 over q outside, and then it will be like this, and you can write in this form, because th2 minus tc2 is theta 2, and th1 minus tc1 is theta 1. So this you can write, and then rearrange this ua by equal to theta 1. So finally q become ua theta 2 minus theta 1 by ln theta 2 by theta 1, and this is actually can be represented this expression by ua q equal to ua theta m. That was the original equation we have already discussed, right? One slide back. So actually you can see that mean temperature difference theta m can be represented by this, and this is actually known as logarithmic mean temperature difference. Okay, so that's the different derivation. You can derive this similarly for counter current heat exchanger, and you'll get the final equation same. Now let us look into overall heat transfer coefficient in a heat exchanger in which two fluids are separated by a plane wall, as I showed in figure 10.11. As you can see, uh, the overall heat transfer coefficient is given by this expression equal to u equal to 1 over 1 by hi plus L by k 1 over ho, where hi and I and O stands for inside and outside. Now if the fluid are separated by tube wall, the overall heat transfer coefficient given by for inner surface and outer surface. Let's just look into tube wall. So this is a tube wall. Okay, so we have a inner surface and outer surface. The thermal conductivity of that tube is given by K, and inner surface radius Ri, outside let's say Rho. Temperature inside is given by Ti, outside given by To, and convective heat transfer coefficient at the inside and outside given by Hi and Ho. Then it is given by this formula: inside inner surface temperature, overall heat transfer coefficient for inside, and overall heat transfer coefficient outside given by this expression, where UiAi equal to UAO, and Ai is a 2 pi RIL and AO is 2 pi R0L, right? I think you all know this expression. This is the best similar expression you have already derived. Now the thing is that the most important is called a concept known as fouling, or actually it's a scaling. Fouling is actually what happens in a heat exchanger with the continuous operation. Some sort of shooting or okay ash darts get deposited. Right? Actually, it's kind of a rust or scale. So what happens when the scale or rust form? This is actually known as fouling, and due to this, the thermal resistance actually increased, or the thermal conductivity or heat exchange capacity decrease, right? So it is difficult to ascertain of this thickness and thermal conductivity of this scale. So the what happens that we actually come out with a strategy where actually we determine the scale heat transfer coefficient. You can see it is given by HS, and HSI and HSO actually scale heat transfer coefficient for inside and outside respectively, inside and out. which is actually related to the thermal resistance for inside and outside, given by RSI or RSO is by this expression, right? So this fouling factor actually comes into play, which will come to the next slide. So RSI is actually 1 over AI HSI and RSO is 1 over AO HO. And the reciprocal of the scale heat transfer coefficient, that is 1 over HSI or 1 over HSO, that is actually scale heat transfer coefficient, is known as fouling factor, okay, which is having unit of meter square degree C per watt. So fouling factor actually determined experimentally by test exchanger in both the clean and dirty condition, and it is given by the difference of the inverse of overall heat transfer coefficient of dirty pipes and the clean pipes. Okay, and some typical value of fouling factor are given in the 10.1, and the representative value of overall heat transfer coefficient given 10.2. This is 10.1 and 10.2. You can see the fouling factor table for different fluid properties are given. It's a very low number, but actually it is going to badly affect the overall heat transfer coefficient and the heat exchanger capacity also. And this is the overall heat transfer coefficient for different fluids and flowing through different medium. So this is actually useful table for determining the determination of fouling factor. Now, when we actually consider the heat transfer, considering the thermal resistance due to scale, which we actually express this expression, the same concept. Only thing you can see, we are multiplying with this HSI, that is actually the scale heat transfer coefficient for inside, and HSO, that is scale heat transfer coefficient for outside. This is standard expression, right? We have already seen, right? This is the standard expression. Uh, because you are multiplying ui equal to by area, right? This is standard expression. This concept is same, but only this term and this term comes into picture due to the scale factor or scaling. Now, overall heat transfer coefficient based on inner and outer surface of the inner tube are given by this. So this you can see, this is the expression, original expression. Okay, overall heat transfer coefficient inside and outside. When actually you have scale, then scale factor comes into play. You can say RF and RFO comes into play. So these expressions are actually very useful when you solve numericals, and thermal resistance due to tube wall thickness and scale. If you neglect, then overall heat transfer coefficient based on the other outer surface given by 1 by HI plus 1 over HO. All the parameters are actually neglected. And inside also it will be 1 over HI plus 1 over HO. And if you fouling factor are only neglected, then it's become like this, because now we have neglected the fouling factor RFI and RFO. So this expression, this 10.28, this term get cancelled, then it's become like this, right? Just only the second and fourth term got cancelled. Now, the overall heat transfer coefficient depend upon following factors: flow rate, properties of the fluid, thickness of the material, as you know, and geometrical configuration of the heat exchanger. Most important is that fouling process are actually, I don't want to go into details about fouling, but you should know that fouling occurs due to various reasons. The most important is corrosion fouling. So marine fouling happens in the ship hulls. Okay, that's a huge industrial problem that is known as biological fouling. The fish foulings are there. And what are the parameters which affect the fouling? Mainly the temperature, velocity, the environmental condition, the chemistry of the water, okay, the properties of the materials which are actually prone to corrosion or prone to formation of scales. So there are various reasons which actually contributes towards the formation of foulings. How do you prevent the fouling? There are various methods. The most important are actually a design of a proper heat exchanger so that fouling can be minimized, or some sort of water treatment can be done to prevent fouling, or some sort of coating, like some strategy, some super hardwood materials are also being developed to prevent fouling, or using a clean system where actually no darts or can shoots or deposit can form. So this is actually the fundamental things which I've discussed at the derivation. I will going to go with a couple of numericals. The numericals are very straightforward, and I'll give you a couple of assignments for today's class. But let us first examine a couple of numericals so that it becomes easy for you and you get familiar with the terminology. Let us first look into the first solved problem. We given the flow rate of a hot and cold water streams running through a small parallel flow heat exchanger are 0.2 kg per second and 0.5 kg per second respectively. That is the mass flow rate. The inlet temperature of the hot and cold sides are given 75 and 20 C respectively. The exit temperature of the hot water is 45 C. If the individual heat transfer coefficient on both sides are 650 watt per meter square C, calculate the area of the heat exchanger. So we have to calculate the area. So everything is, all the parameters as you can see listed here. Now heat transfer rate is, we already saw the know the expression Q equal to mh cph th1 minus th2. You can use even for the cold fluid mc cpc also, same concept you'll get. So you already all you know, so you just put this value and get it. The heat loss by the hot water is similarly heat gain by the cold water. So these expressions are, we put this value and then calculate TC2. That was not given. To TC2 is 32C. Now, this is a parallel flow heat exchanger, I guess, running through parallel flow. So the expression will be theta m theta 1 minus theta 2, ln theta 1 minus theta 2. But this theta 1 is actually the inlet temperature. For parallel and counter, it will be different. So please look into this matter. For counter current, for parallel flow, it will be TH1 minus TC2, TC1, theta 1. But for counter current, it will be TH1 minus TC2 because counter current comes from the right to left, the cold fluid, and hot fluid goes from left to right. So familiar with this terminology. So you just put this value and calculate theta m. And then the expression, the heat transfer coefficient U can be calculated from the relation 1 over U, 1 over HI plus 1 over HO. So HI and HO are same. It's been given, right? For 650, right? I guess both sides given. So U is actually calculate 325 watt per meter square C. And the general expression Q equal to UA theta M. So theta M area U know. So you can, sorry, area you don't know, you know, theta M and Q also been calculated. So you can calculate area 2.66 meter square. Next example, a counterflow double pipe heat exchanger using superheat steam is used to hot water at the rate of 1050 kg per hour. The steam enters the heat exchanger at 180 C and leaves at 130 C. The inlet and exit temperature of water are 30 C and 80 C respectively. If overall heat transfer coefficient for steam to water is 814 watt per meter square C, calculate the heat transfer area. What would be the increase in area? So heat transfer rate is given, the mass flow rate is given 2.917 kg per second. Inlet temperature given hot fluid 180, outlet uh, hot fluid 130. Inlet for cold given 30 and outlet given 80. Overall heat transfer coefficient given 814 watt per meter square C. So when the fluid flow is counter, theta m will be theta 1 minus theta 2, ln theta 1 by theta 2, same. Now in this case, theta m is theta 1 minus theta 2, all the temperature is given 100 C, right? So this is for the counter flow, this is for the parallel flow. The counter flow, you can see the inlet theta 1 will be TH1 minus TC2, that is theta 1, and theta 2 will be TH2 minus TC1. Now as you can see that theta 2 is 100, theta 1 is also 100. So in that case, because then it will become 0, what you have to do, then if it is theta m, theta 1, theta 2 same, you have to take the average, arithmetic average. So theta 1 plus theta 2 by 2, or you can say theta m is theta 1, theta 2, 100 C. So the heat transfer is given by Q UA theta m. Q is still m dot C CPC TC2 minus TC1 UA theta m. But put this value and then calculate area to 7.5 meter square. Now when the flow is parallel, theta m will be theta 1 minus theta 2, ln theta 1 by theta 2. Now in this case, it is not theta 1 and theta 2 are not same. Now theta 1 is 150 and theta 2 is 50. So you can calculate this and then you get theta m 91 C. So you can see theta m for counter current is 100 C, theta m for parallel flow is 91 C. It's not equal. So then again express the similar expression and then calculate area. That is 8.24 meter square C. So the increase in area is 9.87%. So the what is the most important take-home message from this numerical is that, as you can see that for counter current, the similar amount of heat exchanger happens over an increased surface area. So that's why the surface area advantage is always there when there is a counter current flow, because counter current require less area for the similar amount of heat transfer, whereas parallel flow you need a higher amount of area, 8.24 meters square. So that's why I was mentioning in the initial slide that counter current is much more economical and much more advantageous compared to the parallel flow. This is the reason, because over a small area you can have a much more higher heat exchange compared to the parallel flow. Okay, so I hope you understand from this numerical. You can go back and look into this numerical and understand the fundamental difference. Let us look into another example. A counter flow heat exchanger through which passes similar constant 12.5 kg per second of air to be heated from 540 to 146 C. Sorry, to be cooled. Contains 4,200 200 tubes, each having a diameter of 30 millimeter. The inlet and outlet temperature of cooling water are 25 C and 75 C respectively. If the water side resistance to is negligible, calculate the tube length required for this duty. Turbulent flow inside the tube. Nusselt number is given. Specific properties of the air at average temperature are as follows. Cp given, all the parameter mu and thermoconductive given. So first is mass flow rate, inlet temperature, outlet temperature for hot and cold fluid, number of tubes given, diameter of the tube given. So length of the tube, first you have to get Reynolds number, that is d0 by mu. Mass flow rate it can be written in this form: mass flow rate into number of tubes, area, volume, density, right? So therefore del V Vp will be m by Na. So Reynolds number you can substitute dV rho by mu, right? So actually you can substitute uh, I guess the velocity, right, equal to by m by Na. So m by Na mu, because then you can calculate the Reynolds number this much. Prandtl number you calculate 0.6966. Nusselt number will be hd by k, because the expression is given. The Nusselt number hd by k you can equalize and then calculate h, which is kd by 2 to kd by d into 221.2. K is also given, I guess, 3.03 into 10 minus 2. The D is also known. So H you calculate 21.22 watt per meter square C. Since the water side resistance flow is negligible, so you inverse of overall heat transfer coefficient will be only 1 over H, because 1 over HI or plus 1 over HO, one side is negligible, so it will be only inverse. So overall heat transfer coefficient 21.22 watt per meter square C. LMTD you calculate for a it is counter current flow, so you can calculate 250.5 C. Then further heat transfer rate Q will be this much UAM, and A will be 2 pi n pi dl, because n is the number of tube, pi dl is the surface area. So that is the total surface area over which the heat transfer happens. So then you can calculate from this expression L, length of the tube, because all the parameters are known, right? Mass flow rate given, Cph is known, Th1 mass Th1 no. U also already you calculated. N is the number of tube, pi diameter of the tube, and theta m also calculated. So the length of the tube will be 2.31 meter. So this is little different numerical. You have to calculate the length of the tube, but the expression and all the things are very similar. If you go through this slide, you can easily understand. I think last numerical is a cell and tube counterflow heat exchanger. Water flows through a copper tube, 20 millimeter ID and 23 millimeter OD, while oil flows through the water center at 20 C and comes out at 30 C, while oil enter at 75 and comes out at 60 C. If the water and oil side flowing coefficient are given 4500 and 1250 watt per meter square C respectively, thermal conductivity of the tube wall is 355 watt per meter C. The fouling factor on the water and oil side may be assumed to be 0.004 and 0.001 respectively. If the length of the tube is 2.4 meter, calculate the following: the overall heat transfer coefficient and the heat transfer rate. So all the parameters are given: D1, DO, inside diameter, outside diameter, inlet temperature of the cold fluid, outlet temperature of the cold fluid, inlet of the hot fluid, outlet of the hot fluid, specific heat transfer coefficient inside and outside, thermal conductivity, fouling factor. So overall heat transfer coefficient, like this expression already have seen, right? One of U naught was this 1 over this, so 1 over U naught will be this, equation 10.28. So you can calculate U naught equal to 396.8 watt per meter square C. That was the overall heat transfer coefficient from now. The heat transfer rate will be A0 pi G0 L. L is known, T0 also known. You calculate the LMTD, you calculate LMTD, and then you calculate Q. That is U0, A0, theta m. U0 calculated, A0 you calculated, and theta m you calculated. That is very simple. The expression is given. Only thing is that this expression where you have to calculate the overall heat transfer coefficient based on outside area. Okay. So this expression you have to remember, or if it is required, I'll provide you during the exam also, not to worry. Okay. So I have given you here two example, I guess two numericals I have given. Please solve it, and in the next week's class, it will be due. And first example is very simple. You have to just consider parallel from counter flow. Second example is just like the one I solved, because the expression is given. All the parameters are given. So you have to calculate the length of the tube. So you can go back the solved example which you have done now, and then using the same concept you can solve this too. Thank you.